And today's lesson is about weight. Let me pull this over so we can all see it. And you guys probably have it up too. All right, so here on our lesson we have, what kind of flag is that? It's a Japanese flag. So we've got, and it looks like they're all three Japanese. Correct me if I'm wrong. And where are they, do you think?
In space.
In space. Wait, are you sure? Do you really think the Japanese could get 3 Japanese astronauts on a mission all together? Oh, so they're not actually in space. The zero gravity plane. So if we roll down here, scroll down, it says astronauts in training often fly on the KC-135 training aircraft to experience near weightlessness. They're not in space. They're trying to... Why wouldn't you ever, at least not now or in the past, see 3 Japanese astronauts up on the space station together at the same time? Who's the numero uno investor in the space station? The International Space Station. Huh? No, not a penny. He runs a private company. Said Elon Musk. No. It's called NASA, which is what country? Us, U.S., yeah. So the Japanese contribute to, the Germans contribute, the French contribute, the English contribute, a bunch of countries contribute to the International Space Station, but to have an entirely Japanese crew would be highly unusual, very unlikely, just like you wouldn't normally see an all-American crew. Usually you're going to have maybe a couple of U.S. astronauts with somebody from France or somebody from Japan. Anyway, off the mark, or off topic. They experienced near weightlessness. Now the KC-135 has an AKA. You guys know what AKA means? Also known as. Okay, so the also known as for the KC-135 weightlessness, near weightlessness trainer aircraft. Does anybody know it? It's called the Vomit Comet. You've heard that before. Okay, why would they call it the Vomit Comet? Because the plane's flying, right? It gets up to altitude, and then it does a series of these. So every time it's doing this part, the plane is falling at the same rate as the people inside of it. So the plane is really just there to do what for the people inside of it that are falling? If the people were falling at the same speed outside of the plane, what would they be experiencing? They're experiencing gravity either way. What? Air resistance. By golly, Porter, if you're falling outside of some kind of... The aircraft is breaking the wind for it, right? It's breaking through the atmosphere. So from inside the aircraft, the people are falling at the same rate as the aircraft, but there's no air resistance. So there's a feeling of weightlessness, even though they're not. Does that make sense? They're in free fall, but there's nothing pushing back on them. So you feel like you're weightless. Has anybody ever driven on a highway and gone over a little hill a little too fast? Maybe not so much that the wheels of the car come off the ground like Dukes of Hazzard style,
Feels like it.
but do you feel your whole body kind of like, ooh, just for a brief moment? Maybe your stomach at least. Anybody deal with motion sickness? Like if you're in a car and somebody's driving like a wild person, you might get upset tummy. Okay, so that's what you're feeling, right? So that's why it's called the Vomit Comet, because they just repeat it over and over, and then they feel like they're weightless. They look like they're weightless too, by the way, if you had a camera in there. Which is why, anybody ever watch sci-fi movies that take place in space? Anybody? Nobody? Okay, a couple of you. Okay. When they're filming those scenes and it looks really realistic and then stuff's floating, pencil in the air, whatever. A lot of those scenes, if they don't do CGI, they're filming it on the Vomit Comet. and they do green screen to make the background look different than the aircraft. Does that make sense? But they're doing it in the vomit comet. Anyway, that's cool. I am not on that. Here we go. What's the relationship? This is the question for today. What is the relationship between mass and weight, which is what you were writing down, right? You guys were trying to write down definitions of. I'm kind of guiding you through, so we're going through this, but I'm the kind of teacher that likes to be more hands-on. Mass of an object is defined as the amount of matter in an object. Does the amount of matter in an object change if you move location? Even if you move into space, does your mass change? Even if you go to Jupiter, does your mass change? Okay. Does your weight change? No? What causes weight? Gravity. Some sort of gravity, whether it's Earth's gravity, Moon's gravity, Jupiter's gravity, Io's, whatever. So, write this down. We have I don't want to use that one. I want to use a dark marker that shows up well. Force equals mass times acceleration, you guys. You're going to use this a whole bunch this year. Force equals mass times acceleration. And force in science is measured in newtons. Newtons, capital N. Capital N. What do you think the M is for? Mass, and mass is measured in, anybody? Kilograms. kg for short. And finally we have acceleration. I don't need to write acceleration. I don't know why I'm breaking with our format. I do it all the time. What's acceleration measured in? You definitely should know this one after last unit. Acceleration is measured in what units? Boom, meters per second squared. And you even got the squared part on the end. The other classes, they're like meters per second and squared, right? Good. Now, in this text, you might see force substituted for, instead of an F, it'll say a W. Well, isn't weight caused by a force? Right? Isn't weight a force? Yes. So if you see a W instead of an F, the weight is still going to be in newtons, because a weight is a force, isn't it? If you have a weight on top of you, isn't it going to like crush you, push down on you with certain force? Okay, good. So weight is a force, and we measure it in newtons. The M would still be M for mass, so it'd still be, this would still be N, this would still, you might see a G instead of an A. Why might you see a G instead of an A? What's the A? Acceleration. What's the G? Gravity. Acceleration due to gravity. So it's the same. You're just using that interchangeably again, okay? So you might see G instead of A. Now, the difference is the mass is going to stay the same all the time. This is fixed. Because whether you're on the Earth, the Moon, middle outer space, whatever gravitation you're being influenced by, the mass stays the same. Are we clear? Yep. The question is, what's the relationship between mass and weight? Mass always stays the same. Weight depends on the acceleration due to whatever gravity it's being influenced by. So for example, we're talking about where. Gravity where? If we're talking about gravity on Earth, what's the acceleration? Huh? 9.8 meters per second squared, right? I'm making a list, but they're all going to be in meters per second squared. Okay. On the moon, the gravity is 1/6 that of Earth's. Could somebody tell me what kind of math we would do then to determine the gravitational acceleration on the moon? If it's 1/6 of that on Earth. You what? Divide. By what? 6. So everybody, 9.8 divided by 6. How many times does 6 go into 9? Once. 6 times. So 9 minus 6 is 3. Can 6 go into 3?
Yes, once.
Nope, can't go in there at all. Not even once. So we're going to drop the 8 down. Woo. How many times does 6 go into 38? 6 times. 6 times 6 is 36. Subtract, what are we left with? 2. 38 minus 36 is 2. Last time I checked. And then, wait, we can't put 6 into 2, so we got to put a 0 here. Drop that down. Let's 6 into 20, how many times? Whole, 3. 3 times 6 is 18. What do we get when we subtract that? 2, right back to where we were here, so this is going to be another over and over and over again. 1.63 meters per second squared. Put it right here. That's the moon. There is a multiplier. All right, I'm going to give you the multiplier, and you're going to give me the acceleration due to gravity. All right, so 9.8, we're going to do Mars. 9.8 is Earth's. The multiplier is 0.38. So 9.8 times 0.38. First one to get it, raise your hand. You got a calculator there. Go. 3.7 what? 3.72 meters per second squared for Mars. All right, let's do another one. Jupiter. Jupiter's gravity. You take 9.86 meters per second squared for Earth times 2.36. Go.
23.1.
Say again.
23.12.
23.12 meters per second squared for Jupiter. You guys want, how about Pluto?
Not a planet.
Ah, I didn't say it was. Moon's not a planet either. But we'll take it just for fun because everybody likes Pluto, the dog, right? You could. Wow. Shh, get this one. So you're going to take Earth's 9.8 times 0.007. 007's planet, I guess. Or dwarf planet. And somebody different. 9.8 times 0.007. Garvin?
0.0686.
0.0686. I'll round up to 0.07. How's that? Okay. Wow. So the moon, our moon, has more gravity than Pluto by a sizable margin. That's wild. That is wild. Okay. So, something seems wrong in my mind with that. But I'll trust the numbers for now. But somebody let me know if you guys work that out later, if you guys look that up. Something's wrong here. And I want you to find your weight on as many of these bodies as you can in I'm going to give you 5 minutes. You should be able, hopefully, to get all of them, okay? So in your notes, you're going to say weight. You can make a little chart on ... right? And then you're going to have, this is going to be in newtons, right? In newtons. Weight on Earth, weight on Moon, Mars, and Jupiter. I don't think we need to do Pluto because I don't trust that number right now. I'll have to look. But I think it'd be about the same as Moon. Anyway, so do those 4. What do you need, though, before you can do any of them? We're looking for the weight, which is the force in newtons, it's equal to what? Blank times blank. What? What is M? What's M? Mass, and it's fixed no matter where you go. So we got to decide the G or the A, the acceleration, is given to you here for each one, right? What is your mass? So do me a favor, go on Google and say, hey Google, what is the conversion factor to go from pounds to kilograms? And it should give you two ways of doing it. You could multiply by a conversion factor to get kilograms, or you could divide pounds by a certain conversion factor. So it should give you two ways to get there. Nora, what do you got? Yep, take a pass. Anybody find it yet? What's the conversion factor or factors? How to get from pounds to kilograms? Did anybody pull up a calculator? Like literally in Google, just say pounds to kilograms. What's it say? What is it?
0.45359.
0.453. We'll stop there. So 0.453 times your weight in pounds is going to give you your mass. Because your weight depends on where you are. The conversion factor relies on the knowledge that we are here on Earth. Or you can take your pounds divided by what? Anybody see that one? It was 2.2. Okay? So for me, I'm 220 pounds because I like snacks. And I don't like exercise, so I'm 220 pounds. I'm about 40 pounds overweight, y'all. 40 pounds. That means I'm obese. That's not my words, that's my doctor's words. He says, you are now obese. Congratulations. Maybe you should do something about that. And I'm like, yes, I should. He's are you gonna? I'm like, sure. Okay, so 220 for me divided by 2.2 is really convenient because that's just 100, isn't it? So for me, I'm gonna have force, my weight in newtons, equals my mass, 100 kilograms. You're going to plug in your mass there, right? You get your mass by taking your pounds divided by 2.2, or your pounds times 0.453. And then I'm going to multiply that by 9.8 meters per second squared if I'm looking for my weight in newtons on Earth. So I should be plugging in over here, shouldn't I? Equals 100 kilograms times 9.8 meters per second squared. And I get, my numbers are super easy because I can just move my decimal over. So 980 newtons. So what do I do for moon? Is my mass going to be any different? No different. So I'm going to put my mass here. By the way, don't put my mass, put your mass. For your mass, you take your pounds times 0.453 or divided by 2.2. Okay? All right. So my mass times acceleration due to gravity on the moon, 1.63 meters per second squared. And I get, again, easy numbers for me, 163.3 newtons. All right, so in your notes, go ahead and complete that table for you. And while you're doing that, I'm going to look up this whole gravity on Pluto thing because I pulled that right out of a textbook.
0.62.
Huh?
0.62. That's
what it is? Acceleration due to gravity? On Pluto? You already looked it up. That's awesome. 0.62? So that textbook I'm using is either wrong or I did something wrong. Check Jupiter for me. See if my number for that's correct. So our numbers are off a little. No. Just use what's there, okay? Use what's there. Why do you think our numbers might be off? Huh? Not updated. So do we think that maybe when the textbooks that I was using last year were made, back before the year 2000, do you think scientists have better estimates on the mass and therefore the gravity of Jupiter?
Yeah.
Oh yeah. Oh yeah. And 23.2, and you said it was what? 26? That's a pretty sizable change. And my guess is it's the same reason for Pluto, because since the textbook was written, we had New Horizons. Anybody hear about New Horizons? That was a mission that was specifically for getting to Pluto. So I'm sure they must have taken better readings on it. Pluton. Wait a minute, what the heck is Pluton? No. Did you put that down? Did you just blindly copy what I wrote? Did you write Pluton?
Yeah.
I mean, it's my mistake. You were just repeating it. Call me out on mistakes, y'all. You gotta be awake, because sometimes your teacher, I mean, he's a human being. All right, so I'm gonna go ahead and finish mine, because they're all easy for me. Because and for you, again, the kilograms stay the same, right? And we're just multiplying by the different acceleration factors. So Mars, 3.72, so I would be 372 newtons. And this is Jupiter, 3.12, be 2,312 newtons. Y'all think it'd be easy to stand up on Jupiter?
No.
Not so much. You'd be able to do it, but okay, so 2.36 times, actually more than that with the updated, 2.5 times what you weigh now. So I would feel, if I'm about 200 pounds, 2 times that would be 400 pounds. We're like and a half. So I'd be over 600 pounds? About 500 pounds. Do you think I'd be able to stand up if I weighed 500 pounds? I think I could, but I mean, I would be at my... Anybody ever do leg presses? Right? I mean, imagine standing as a 500-pound person. People do it. There are a few out there. So it'd be a very difficult go, though, wouldn't it? So, I mean, think about it this way. I'm 200 pounds. I'd have to have another 300 pounds on my back. Could I give a piggyback ride to a 300-pound person? Yes, but I'd be hurting the next day, right? And I wouldn't be able to do it for very long, would I? No. All right. Did you guys have all your weights in newtons? Good exercise. Not exercise like this, but exercise up here. All right, so moving on. Let's get back to our CK12 lesson. Do we see the relationship between mass and weight? That was the point of this. And just kind of have fun. There's your mass, balance. You guys can read that. Weight of an object is a force pulling the object downward on Earth. Yep, we just did all those. 1/6 for the weight on the moon. Gravitational force is derived from Newton's second law. Force equals mass times acceleration. We went through that. We used it several times. Good practice. And yes, this is important. Put this in your notes. You say I can erase this?
Yeah.
All right. Put this somewhere in your notes that's like important information that you'll use over and over. A Newton, 1 Newton is equal to 1 kilogram times 1 meter per second squared. And I'm going to like draw a rectangle around that. And I'm going to switch colors and draw a rectangle around that just to, that's important. Okay, that's important. And here I'm going to show you an example of how it might be important. In this problem right here, it's asking what the mass of an object is whose weight sitting on Earth is 2,570 newtons. So I'm going to put it in our force equals mass times acceleration formula, go ahead and do that too. So 2,570 newtons is equal to the mass, which is what we're looking for, times acceleration on Earth, which is 9.8 meters per second squared. Everybody follow? We're working this problem right here. Does everybody understand we're working this problem right here? Okay. Well, I'm not getting any feedback from you, so I just want to make sure you're awake. So I'm putting it into my force is equal to mass times acceleration with the information I have. What do I have to do with this formula to find mass? What's the first thing I need to do? Times. What times what? M times what? Mass times what? But I can't because I don't know what M is.
Mass.
So yes, it's mass, but what is mass? See what I'm saying?
Weight.
No, mass is not weight. Weight's over here.
Oh, volume that it takes up. Like,
No, we're not looking for density. Guys, mass. Look at this as an algebra problem. Okay? This is an algebra problem. It doesn't even matter that M is mass. What is M? It's a variable. Who said that? Is that you? Good. M is a variable. You can't multiply a variable by a number to get a number. You have to do what to it first? In this case. You're saying it, say it louder.
9.8 divided by 2,570.
And 9.8 divided by what?
2,570.
You just said that. And 9.8 divided by what? The whole point of dividing this by this is to find this, right? But you're skipping a step. The whole point, I gotta get M by itself before I can solve for it, right? What do we call that in math? We need to blank the variable. Isolate the variable. How do I get the variable by itself? If we're multiplying the variable times this, to get this out of here, I need to do the opposite of multiply, which is to divide. So first, I'm going to divide this side by 9.8 meters per second squared so that it eliminates. It doesn't eliminate right away either, actually. Doesn't 9.8 divided by 9.8 equal 1? Don't say no to me. You immediately questioned yourself, didn't you? What is any number divided by itself? 1. Unless it's what? 0. You can't. Something becomes undefined, right? But 9.8 divided by 9.8 is 1. So if I take this and say M times 1, anything times 1 other than 0, isn't it just the thing? So can't I get rid of it? So in effect, you divide it by itself to get it out of there. But if I did it to this side, I have to do it to this side as well, right? So 9.8 meters per second squared. What do I get? It tells us right up there. What do we get? What's the mass? Okay, you don't want to read it off the board. What's 2,570 newtons divided by 9.8 meters per second squared? Huh? 262. 262 what? Kilograms. What if I didn't know what the units would be in? Maybe I'm confused. Maybe I've been working too many problems. What could I do? Look it up. Where? Right here, right? Watch this. What's newtons divided by meters per second squared? You don't know, right? What is a newton? Couldn't I replace the N with a kilogram meter per second squared? It means the same thing, right? But now look, I divide it out, the meters per second squared are gone. What's the only unit left? Kilograms are the only unit left. Okay? Now hold on. Last thing, because we're probably running out of time. Last thing, and then you guys can probably have no time to work the problems. I put it in the force equals mass times acceleration, and then we had to isolate the variable and divide it out. In their example, what did they do? They started with isolating the variable. They just put the variable mass by itself. They said, why don't we just rearrange the formula? Mass is equal to force divided by acceleration. Now you didn't have to move anything. You just do the math. Does that make sense? We just have our force, 2570 newtons, divided by our acceleration, 9.8 meters per second. It's the same thing, but kind of simpler. I get confused with math though, so I just usually stay with what I know and then isolate the variable. So do you see how you can do the same thing by just isolating the variable to begin with? Okay. It's the same formula, just rearranged to look for a different variable. Questions, comments, concerns? You guys, we did pretty much everything in there. You can look over the summary, the review. There's a video that's okay. This simulation is not particularly valuable. You can look through it anyway if you'd like. Do the practice, turn it in, just do tomorrow. But if you can get it done today, isn't that better?